the transformation matrices, right? So we had these three coordinate systems. We had the Cartesian, cylindrical, and spherical. We'll work on some example problems in transforming vectors and points in one coordinate system into another. Okay. So I'm kind of going to sound like a broken record here. So there's a lot to take in, right? So far in the topics of vector algebra, and we haven't even dug deep into vector calculus yet, right? Now this is not an advanced level mathematics course, right? A lot of this stuff is being taught by mathematics professors, and my background is not mathematics, right? So what we are doing here is we are equipping ourselves with tools that we will need to understand electromagnetics, which will start in chapter 3 and subsequent chapters, okay? So try to absorb the material, and like I said, there is no substitute for going home and working with the material yourselves, right? If you adopt the attitude of the teacher will teach me, I can only do so much, and it's going to be very tough for you to not only do your midterm on these kind of problems, not only that, but when we get into actual electromagnetics related topics, to solve those problems, to understand those concepts, will become very, very challenging if you don't put in the effort up front on chapters 1 and 2, okay? So I've hopefully adequately informed you. So I'm also speaking a little bit from personal experience, right? When I did my own undergraduate introduction to electromagnetics course, it was very similar. Obviously not at this university, but the material is very similar, right? Now I would typically have, my university, we would have 3 midterms and 1 final, right? So here it depends on the professor, the instructor. But when I did my undergrad, it was all, what can I say? The template was the same, right? All courses, all 4 years, 3 midterms and 1 final. Yeah. So I was the type of student who studied each subject 4 days a semester, right? 3 midterms and 1 final, right? So I will tell you, I could get by with getting A's and good grades, studying 4 days a semester each subject, right? So if I had 5 courses, I would sit down and study maybe 20 days a semester, right? Not very proud of it. I'm not suggesting that you do it, but what I'm trying to say here is that method, it really did not work for my electromagnetics course, right? I had to really struggle. What's that?
Because it builds.
Sorry?
Because the subject matter builds upon each other.
It builds up, and I mean, you will see, right? So if I go to go like this, right? Right, look at this. Do you really think you can sit down the evening before the midterm and understand what's going on here? It's just not possible, right? So once again, maybe some of this material is very familiar to at least some of you, so maybe it's possible for some of you to do that, but it's not recommended, okay? So spend time working with the material at home, and if you have any specific pain points, we can work through them. We can maybe have a session discussing those topics again. But let me jump into the problem. Anyway, enough beating that dead horse, right? Right, yes, so as I said, the problems here are going to be primarily in the various coordinate systems and the transformations. Yeah? So the first one, this is an example problem, so you could review the textbook as well. We have 2 points in the cylindrical coordinates system given as P1 is R1, P1 and Z1, and P2 is R2, P2 and Z2. Now find the expression of the vector pointing from P1 to P2. And firstly, in the Cartesian coordinate system, which is x, y, and z. Right? So what we need first? First we need the expressions for a point in the x, y, z coordinate system, and the right hand sides have to be functions of r, phi and z. Okay, r, phi and z. Now we could keep jumping back and forth. So if I go back here, so what are we looking for? We are looking for the expressions for r, phi and z in terms of expressions for x, y and z in terms of r, phi and z. So if I go to right, there we have it. So we have the Cartesian coordinates x, y, z in terms of the r, phi and z coordinates, right? So we did this in the previous lectures. So I'm just gonna repeat that here. X equals r times cosine phi. Y equals r times sine phi, and z equals z is just c. Yeah. And there are 2 points, x1, y1, z1, and x2, y2, z2. So what does that give us? I can just write there. X1, y1 and z1 are r1 cosine phi1, y1 is r1 sine phi1, z1 is just z1, x2 is r2 cosine phi2, y2 is r2 sine p2, z2 is z2. Alright? And in the Cartesian coordinate system, you want to get the vector that connects 2 points. It's a simple subtraction between the coordinates. So the vector, let's call the vector A in the xyz coordinate system equals in the x direction, what do we have? X2 minus x1, right? X2 minus x1. So that would be r2 cosine phi2 minus r1 cosine phi1. So that's the x coordinate. Plus, in the y direction we have r2 sine phi2 minus r1 sine phi1, plus in the z direction we have z2 minus z1. Okay, that's it. That's the vector that connects point P1 to point P2 in the Cartesian coordinate system. Okay.
And B is do the same in cylindrical coordinates. That would be R, phi, and Z.
Now, in the cylindrical yeah.
I just wanted to make sure that it's standard, right, for it to be R cosine for X every time in the cylindrical?
Well, you need to choose your convention the way we did when we did that derivation, right?
Right, I'm just saying.
Yeah. So what is our standard
Because that would be-
practice? Z is the altitude axis, so we preserve that if you remember. Yeah. And then X, Y, and Z form a right-handed system, right? Remember the right-handed system? So if I can draw up here. So you have the x-axis that way, y-axis this way, right? And because this is a right-handed system, Z is pointing upwards. Yeah. Yeah. Now that's the Cartesian coordinate system. The cylindrical axis, right? Initially, the R is aligned with X. Right, you need to perform that initial alignment, and then the R-axis is rotated counterclockwise. Remember, so that results in the R-axis being somewhere here, and theta is going counterclockwise. Right, so that would be I'm sorry, not theta. That's phi. That's phi, and Z is the same as the Z-axis there. Right. So as long as you assign your axis this manner, these expressions are valid.
And that's just the standard, like, unless otherwise specified, that's the way it is.
Well, the convention is to use the right-handed system, isn't it? The convention, when you choose Cartesian coordinate system, you don't choose the left-handed system, you choose the right-handed system. So the way I've drawn the blue axis, right? Now there's nothing in the nature that says this is where it should be. This is convention. We choose the right-handed system by convention. If you mess that up, there'll be negative symbols floating around. So you need to be careful about that. Yeah. So now we have a vector which is in terms of x, y, z components, and we need the vector in a cylindrical component. So that would be AR, A, P, and AZ. Equals, okay, and on that side we have A, X, A, Y, A, Z. Now remember those transformation matrices to go from X, Y, Z to cylindrical and vice versa. So if you go back to the course notes, this matrix looks like this. So you have cosine phi, sine phi, 0, minus sine phi, cosine phi, 0, and then you have 0, 0, 1. Okay? Now this is what we have. And of course, the AX, AY, AZ vector or matrix is, it looks like, what does it look like? AX, AY, AZ is R2 cosine phi 2 minus R1 cosine phi 1, R2 sine phi 2 minus R1 sine phi 1, and then Z2 minus Z1. Okay, so now we need to multiply this matrix by that vector there. Now, how is that going to look like? We have AR, AV, AZ equals, so this whole term here multiplied by cosine phi. So that would be cosine phi R2 cosine phi2 minus R1 cosine phi1, then plus, right, plus sine multiplied by the second row of that A xyz vector, right, plus sine phi multiplied by R2 sine phi2 minus R1 sine phi1. And what is the next row here? You have to multiply sine phi by the top row, or minus sine phi by the top row. You have minus sine phi by the top row, R2 cosine phi2 minus R1 cosine phi1, plus multiply cosine phi by the second row. Cosine phi times R2 sine phi2 minus R1 sine phi1. And finally you get Z2 minus Z1. Now you can see if you expand this, right? So you have the whole first row is A sub r. The vector in the cylindrical coordinates, the vector A, is you take A sub r, that's along the r directions, plus A sub phi, which is the entire second row along the p direction, plus AZ along the v direction. Okay? What's the third part here? The third part is calculate the length of the vector. What is the length of the vector? Yeah. Now the length of the vector doesn't change if you go from one coordinate system to the other, right? Which means we can stick to, let's say the Cartesian system, and then we say ax squared plus ay squared plus az squared. Yeah? Ax squared plus ay squared plus az squared. And what is ax in the Cartesian form? You have r2 cosine phi2 minus r1 cosine phi1. And what is y component? r2 sine phi2 minus r1 sine phi1. And then finally you have z2 minus z1. Okay? Now, we all know the expansions, these expansions, right? Different color. We know these expansions, a
minus b squared is a squared plus b squared minus 2 times ab.
Okay? So you apply that to the first two square terms, alright? And then you simplify, what you get is square root r1 squared plus r2 squared minus 2 times r1 r2 cosine phi2 cosine phi1 plus sine phi2 sine phi1, and then you have the okay. Then another layer of simplification is possible, because this term, if you go refer to the trigonometric identities, this term you will see that it is cosine phi2 minus phi1. Okay, so the length of this vector is square root r1 squared plus r2 squared minus 2 times r1 r2 cosine phi2 minus phi1, and then you have the z2 minus z1 squared component. Okay? Questions? Okay, I'll publish this in Canvas anyway. The second problem is you have a vector. The previous problem we had a point, and now we had points, and now we have a vector in the cylindrical coordinate system, and now we need to transform this into the Cartesian coordinate system. So which means we need this transformation. So we need ax, ay, az, and on the right hand side we have ar, a, v, and a, z. Now what does this matrix look like? You can once again go back to the course notes, and you will see that it is cosine phi minus sine phi 0, and then sine phi cosine phi 0, and then 0, 0, 1. I don't know what causes those glitches. Okay, so that's our transformation matrix, and we can use that matrix to translate the vector given here, right? A sub r is equals 2, a sub phi equals 3, and a sub z equals minus 1. So the vector on the right hand side is 2, 3, and minus 1. Yeah. So now if we apply the transformation matrix,
we get ax, ay, az equals cosine phi minus sine phi 0, sine phi cosine phi 0, and 0, 0, 1, and the vector that we're multiplying is 2, 3, minus 1. Okay? So we perform the multiplication, what do we get? 2 times cosine phi minus 3 times sine phi 0, sine 2 times sine phi plus 3 times cosine phi, and then we have minus 1. Okay? So far nothing nothing jumps out problematic, yeah? So now we have a vector, right? So you can take this whole term here, yeah? You can take this whole term here and then say x hat. Then the second row, the entire term here, and then say y hat. And then this term, and then say z hat. In fact, let's do that. So a equals, the vector a equals, so the top row, you compare the left hand side and the right hand side, right? So what is a sub x? A sub x is 2 cosine phi minus 3 sine phi. So that would be, in the x direction, we have 2 cosine phi minus 3 sine phi, plus in the y direction, that's the second row there, we have 2 sine phi plus 3 cosine phi, plus in the z direction we have minus 1. Yeah? However, we need the x-axis, y-axis and z-axis scalar components in terms of x, y and z. In terms of x, y and z. So, what is the relationship between the r and the phi and the x and the y? We just had that discussion on the assigning of the axis and everything. So if you do the axis assignment properly, what do you get? Cosine phi is equal to x over square root of x squared plus y squared, and then sine phi is equal to y over square root of x squared plus y squared, right? So if we go back to our earlier point, right? So if I go back to, right, so this is our x, y, z 3-coordinate system, and the cylindrical coordinate system now looks like this. So that's the r, and this the p, and this is the z axis, right? So if this is angle phi, what is cosine phi? What is cosine phi? Cosine phi is the adjacent side divided by r, right? So that's cosine phi, adjacent side to the angle divided by r. So that's r is nothing but square root of x squared plus y squared. Yeah. So now that we've established this, our vector now becomes a vector equals x hat. What is this? 2 cosine phi minus 3 sine phi. 2 times cosine phi minus 3 times sine phi. Yeah, so that's our ax component. Now the y component is, what are the y components? 2 times sine phi plus 3 times cosine phi. So that would be 2 times sine phi plus 3 times cosine phi. Okay, plus z of course remains the same. All right. Any questions? So we didn't reinvent anything. We derived these transformation matrices during the course of our lecture discussions. You go back to the PDF. The top equation is there, and all we've done is applied this transformation matrix, and magically we get the same vector in the XYZ coordinate system. Okay? Any questions here so far? Okay. Give you a minute to very good. So, you know, what have we been doing? You know, in the first problem, we took generic points, and we constructed the vector in Cartesian coordinate system, and then we transformed it into the cylindrical coordinate system. Okay? It's a generic points and the vector connecting the 2 points. Now we have, in the second problem, we have a vector given in the cylindrical coordinate system, and what is the corresponding, the same vector in a 3-axis, in an XYZ Cartesian coordinate system. So that's given here. Now this is, you know, you see the vector in the cylindrical coordinate system. You see it's just a simple 2 times r, 3 times phi, and minus the z, right? But if you look at the same vector transformed into the Cartesian coordinate system, it looks like this. It's full of these variables, x, y, and so on, right? That's because, as you know, if you go back to the discussion, the transformation matrices are not constants. The transformation is a function of the position of the angle, right? Remember that? The transformation is a function of the position, yeah? That's the reason why once you're done with the transformation, you get this kind of a full of variables. So typically, this kind of a problem is presented. So you have a vector in the XYZ coordinates, Cartesian coordinates, and you need to transform that into cylindrical coordinates. But in this case, you're given a specific point. Just like how in the cylindrical coordinate system, the values are dependent on the angle. The same way here, so if you transform this into the cylindrical coordinate system, you can evaluate that vector at a particular point, and that's what we're going to do here. So what we're doing here is the opposite of the previous problem. So we have the vector in the x, y, z coordinates, ax, ay, az, is what we have on the top left, ax, ay, az being 2 minus 5, right? So we have that. So this vector is what we've been given, and what we need is AR, AP, and AZ. Alright, this is what we need, and the transformation matrix, to transform XYZ into cylindrical coordinate system, it looks like this. Cosine phi, sine phi, 0, minus sine phi, cosine phi, 0, and then 0, 0, 1. Right? Right, so now to get the R phi z components, you have to multiply this transformation matrix by the given vector. Okay? That's what we have. And this gives us what? 2 cosine phi minus 5 sine phi. Okay? And then 2 sine phi minus 5 cosine phi. Then you have 3. Okay? So we haven't done anything more than just multiplying that matrix by this vector. So that's what we have here. Yeah? Now, we have R phi z, not as constant numbers, but in terms of theta, the angle. Like I said, the value is a function of the position. Now, how do we get the position? We just did that in the previous example. So we'll repeat that. Cosine phi is equal to x over square root of x squared plus y squared, and then sine phi is equal to y over square root of x squared plus y squared. Yeah. What are these values, x and y? Now that's given by that point, right? So x equals minus 2, y equals 3, and z equals 1. Yeah? So what's cosine phi now? X is minus 2 divided by square root of x squared plus y squared is 4 plus 9. That gives us minus 2 over square root 13. And y is 3 over square root 13. Okay? So, I will repeat that AR, APhi, AZ is equal to, what is this? 2 cosine phi minus 5 sine phi. 2 cosine phi minus 5 sine phi. 2 cosine phi minus 5 sine phi The next one is 2 sine phi minus 5 cosine phi. 2 sine phi minus 5 cosine phi. Yeah, and then we have 3. So we can do the substitutions. 2 times cosine phi is minus 2 over square root 13. Minus 2 over square root 13 minus 5. Sine phi is 3 over square root 13. And then we repeat the same. Substitutions. 2 times 3 over square root of 13 minus 5 times minus 2 over square root of 13. Then you have Z is 3. This is minus 2. Okay, transformation matrix has a minus sign. Okay. Right, so we get a vector now that looks like this. So these numbers, if you evaluate them, you get minus 5.27, minus 4.43, and then 3. So this vector in the cylindrical coordinate system looks like, in the r direction it is minus 5.27, in the p direction it is minus 4.43, and in the z direction it is 3. Okay? So this is the transformation of the given vector up there in the xyz system has been transformed into the cylindrical coordinate system at that given point. Okay? Any questions? If I have made any mistakes, I'm sure you will let me know. Okay, the next problem, the fourth problem of today, it has 2 points in the Cartesian coordinate system, and a vector connects those 2 points. Find a unit vector. The unit